Push a stone with your finger and the stone pushes back on your finger just as hard. That is Newton's third law, and behind it sits his second law, which is deeper than the famous F equals ma you remember. At its heart, force is the rate of change of momentum. Let's build both laws from the ground up. Newton began his study of motion with a quantity he called the quantity of motion. It combines two things, how much matter a body has and how fast it moves. The motion of a whole body is just the sum of the motions of its parts. So double the amount of matter, keeping the speed the same, and the quantity of motion doubles. Double the speed instead, and again it doubles. Double both together, and it becomes 4 times as large. Our modern name for this quantity of motion is momentum. Momentum is a vector. We write it as P equals mv. Momentum P is the mass m times the velocity v. Because velocity is a vector, momentum points in the same direction the body moves. The m here is the inertial mass, the measure of how hard it is to change a body's motion, and the v is its velocity. This single vector packages together everything about a body's motion, which way it goes and how much of it there is. Now Newton's second law. In his words, the change of motion is proportional to the force impressed, and it happens along the straight line in which that force acts. Read that carefully. A force does not set a speed. A force changes the motion. Twice the force produces twice the change, 3 times the force, 3 times the change. And the change always points the same way as the force. If the body was already moving, the new motion adds on when they agree, subtracts when they oppose, and when they act at an angle. The two combine into a single compounded motion, exactly like adding vectors. Let's make that precise. Apply a force to a body for a short time interval delta t. The product of force and time is called the impulse. A vector we write as capital I. And the Newton's law says this impulse equals the change in the body's momentum. In symbols, I equals F times delta T equals delta P. So a force acting over a time interval delivers a kick to the momentum. A bigger force, or a longer push, means a bigger change in momentum. This is the impulse-momentum relation, and it is the second law in its most direct form. Newton also considered forces that act continuously, not in a single kick. To capture the force at one instant, we shrink the time interval. Take the change in momentum, delta p, divide by the interval delta t, and let delta t shrink towards 0. That limit defines the instantaneous force, F equals the limit, as delta t goes to 0, of delta p over delta t, which is exactly the derivative dp dt. So the total force on a body at any moment is the rate of change of its momentum. This is the second law in its truest form. Here is where the familiar formula comes from. Momentum is mass times velocity. When the mass stays constant in time, the mass just comes along for the ride when we differentiate. So the derivative of momentum, dp dt, becomes m times the derivative of velocity, dv dt. That gives us F equals m times dv dt. But the derivative of velocity is, by definition, the acceleration. So the force is the mass times the acceleration. F equals ma. This is the special case you already know. It is not the definition of the second law, it is what the law becomes when the mass is fixed. There's a subtlety that troubles many students. We defined force through the change in motion. So doesn't the second law just define force? If force is only known by measuring acceleration, where's the predictive power? Here is the resolution. The second law by itself is only half the story. What makes it powerful is a separate ingredient, force laws. These come from experiment. Gravity, springs, friction, electric forces, each has its own force law that tells us the force in advance without ever measuring the acceleration. Plug a known force law into the left side of the equation, and the law predicts the motion. That is where the physics lives. Not every force comes from a force law. Some forces we cannot write down in advance. Think of a block sliding along a surface or gas molecules trapped inside a container. The surface pushes on the block, the container walls push on the gas. These are constraint forces. No force law hands them to us. Instead, they are whatever they need to be to keep the motion consistent with the constraint. We find them backwards from the motion itself. The surface supplies exactly the contact force needed to keep the block on the surface, and the wall supplies exactly the force needed to keep the gas inside. Put the pieces together. On the right of the second law sits mass times acceleration, and acceleration describes how the velocity changes. Once we know every force acting on a body, we know its acceleration. That equation, F equals ma, earns a name, the equation of motion, and it is a launching pad. From the acceleration, we can integrate to find the velocity and the position at every future time. And for constrained motion, running it the other way. If we know the acceleration, we can solve for those unknown constraint forces. Now the third law, the most surprising of the three. Newton's words, to every action there is always an equal and opposite reaction. The mutual actions of two bodies on each other are always equal and directed to contrary parts. Whatever draws or presses another is drawn or pressed just as hard by that other. Press a stone with your finger and your finger is pressed right back by the stone with the very same force. This is not a delayed response, and it is not usually obvious because the two forces act on two different bodies, but they are always there and always equal and always opposite. Let's label the pair carefully because the bookkeeping matters. Take two bodies interacting with each other. Call them body 1 and body 2. The force on body 2 coming from body 1 we write as F12. The force on body 1 coming from body 2 we write as F21. Read the subscripts in order. The first number is the source of the force, the second is the body it acts on. Body 1 pushes on body 2, body 2 pushes back on body 1. Two forces, one interaction. We call this pair an interaction pair. The third law states the relationship between them exactly. F12 equals negative F21. The force on body 2 from body 1 is equal in magnitude and opposite in direction to the force on body 1 from body 2. Same size, reversed sign. Notice what this does not say. It does not say the two accelerations are equal. If the bodies have different masses, the same force size produces different accelerations. The forces are the equal pair. The motions need not be. These three laws, together with the force laws, are the whole of classical mechanics, also called Newtonian mechanics. From them, we explain an enormous range of the world, but not all of it. Newton's mechanics breaks down in three places. When speeds approach the speed of light, we need special relativity. Inside the atom, where electrons live, we need quantum mechanics. And at the larger scales of the cosmos, we need general relativity. Newton is the beginning, not the end. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.